Good afternoon, my name is Anir Perez, and in this lab we investigated the concept of harmonic motion using a mass spring system. Harmonic motion refers to a repetitive cyclic movement such as the oscillation of a spring or an object moving in a circular path. This type of motion can be mathematically described using sine and cosine functions, which model how position, velocity, and acceleration change over time. The purpose of this experiment was to identify and measure key characteristics of simple harmonic motion, including amplitude, period, and frequency. Amplitude represents the maximum displacement from equilibrium. The period is the time required to complete one full cycle, and the frequency is the number of cycles that occur per unit time. These parameters are essential for understanding oscillatory systems and predicting motion behavior. This phenomenon is widely applicable in real life. Examples include the motion of car suspension systems, the vibration of musical instruments, and the behavior of waves and electrical signals. Understanding harmonic motion allows engineers and scientists to design systems that either utilize or control oscillations effectively. Thank you.
Hi, the materials that we are going to be using for the lab today are consisting of a hooking apparatus that is then attached to the pole. Then from the weights provided, we decided to use 50 grams to extend the spring, and then use the motion sensor to detect the data. As I am trying to iterate in the scene is that we are currently seeing that the screen is saying that the motion sensor is jittering, even though that the platform is going up and down. It should not be. It should have a consistent of a wave, and we are currently trying to figure out why it is doing that in the first place.
Oh, I see why. It's the actually like when it drop in, it's like straight down. Yeah, that would be good because we can't do this swinging. That's what.
As previously stated in the last lab that we did, it looks like that the computers were not functioning right, and we all had to use our computer to see and look at how the experiment we're doing and getting the data for our results in.
That occur. So it's about 0.5 because we have 3.5 and then 4.
Okay.
About 4. So it's about. You should be able to highlight. I don't know how to use buttons. Yeah, click the highlight button, and maybe if you just select here to here and then see the time.
From there to...
I would start from the bottom of this one and then the top of this one. Sure. Or isn't there like a button where it's like a line and a line?
I know what you're talking about. I thought it was...
I don't know. I thought it was. I don't know. I think there's a back button. Okay. So, 6, minus
Yeah. Okay, let it go.
See, why is it so vastly different? Yeah, top two look fine, but then
The acceleration.
I think it's fine.
Yeah.
That's better than before.
Okay.
I think we should redo the first one though. Our percent error is gonna be jacked.
You're talking about the positions?
Yeah.
Yeah, we'll redo all of the information. So for the amplitude, that's how high it is off the x-axis. So that's just negative 0.19, right? That's what the amplitude is. The frequency, or no, I'm sorry, the period is from there to here, which would be the 3.4 at the beginning, and at the end it's 4.45.
4.45. 1.05.
1.05 for the frequency. I mean period. 1.05. Okay, so
Got a 90%.
1.05. I mean 1 over 0.0.
0.5 or 0.95.
0.95. Okay, no.
That percentage.
Amplitude for the velocity, which would be the negative 0.78. Frequency, repeated period first. So that's from there. So we're going to start negative 0.78 to
Negative.
0.81. Positive 0.81.
Sorry, say that one more time.
Negative 0.78 to positive 0.81. So you're going to do the 1 over 1.59.
0.6.
0.6.
I don't know if the negative sign matters for frequency, but it's negative 0.6.
Okay. What was the other one? Negative 2.
Yeah. Also, what was the amplitude for the 0.78?
0.78.
The percent error for, yeah, that was 50. It was 50.
50?
Mm-hmm.
Okay. 50. Did you do the velocity?
No, I didn't.
Okay.
What was the actual?
The actual, which was the period, right? Was 1.59.
No, for the frequency.
Negative 0.6 for velocity.
But then the actual?
The actual is, I guess, what we get off here, right?
Uh-huh.
Here is the data sheets and results that we all got from the experiment.
Good afternoon, my name is Anil Perez, and in this lab we studied simple harmonic motion using a mass spring system and measured amplitude, frequency, and period. Our results showed that the expected oscillatory behavior was normal, but there were noticeable differences between position, velocity, and acceleration graphs. The percent errors we got were relatively high. For the mass errors were about 370%, 84% for velocity, and 90% for acceleration. For the second mass, they were 50%, 165%, and 1300%. Percent error shows how far our experimental values are from expected values, so these large errors indicate low accuracy. These differences were likely caused by sensor calibration issues, inconsistent release of the mass, and difficulty reading values from the graphs. The high error suggests that while we observed harmonic motion correctly, our measurements were not very precise. And in this lab, we learned how to analyze harmonic motion, calculate key parameters, and understand how experimental errors affect results. Thank you.